All right, well, thank all of you for coming. I apologize for the slightly late start on all of this, but as always, thank you guys for coming to one of our bi-weekly webinars on Green Bank Observatory. So as always, we'll start off these with a little bit of observatory news from my side, and we'll then move over to the feature, which is a talk by Brian Mason from the National Radio Astronomy Observatory talking about long-wavelength measurements of interstellar dust in Orion. So with that, let me go ahead and get started. So just to give you guys a quick update status of what's going on with COVID in the county. So within the state of West Virginia, the number of cases has continued to increase for a while. We're now at 7.8% of all tests are positive for COVID within West Virginia. This is the highest it's been since April, back when tests were really only done when they suspected somebody of being ill. So we're definitely seeing an increase there. Masks continue to be required indoors, and whenever social distancing cannot be handled. Schools have started. They started today's Wednesday, so they started yesterday for within the county and across the entire state. So we'll see how things go from there. On site, as we've been saying all along, the GBT remains in full operation 24 hours a day, 7 days a week, with all of our operations continuing throughout this process. Work is slowly, but it's going slowly but safely, which has been great news for us. Visitor programs remain canceled, but we've had a lot of fantastic Zooms put out by our education group. We've had virtual tours, things like that, which are online, which I encourage you guys to follow our Facebook page if you want to know what's going on and what kind of fantastic new program group is putting together. And we're also working on a plan to try to get some limited tours on site for walking tours, as well as outdoor demos and things like that. I do want to report that we have had our first known COVID-19 case within the staff of Green Bank Observatory. This person contracted COVID-19 through an exposure outside of the work area. The on-site protocols, sorry about the misspelling there, the on-site protocols appear to be working though, and so far at least no other staff have tested positive or shown symptoms of COVID-19. So we're very hopeful that that will continue to be true. We are, however, being very cautious, and a result of this exposure, which did occur for the staff within our machine shop, it's been closed down for 14 days, so it'll be closed until the middle of next week. We'll continue to monitor the situation, continue working with our staff to make sure we've minimized the exposure, but so far the case seems to be isolated at work, which is not good news that anybody is ill, but it is good news that the spread seems to have been stopped within the workplace, which is fantastic. More positive news, I just thought I'd show off this great paper that just came out within the last few days. So I won't read the entire title, but the gist of this was that it was a brand new giant pulse-emitting pulsar that was discovered with the GBT. That sort of thing has happened before. We still like it every time it happens. But what makes this particular pulsar particularly exciting for us is this is the lowest declination pulsar ever discovered with the GBT. So this is down at a declination of about -45.5. And so I just thought I'd show off the great paper that just came out. Appreciate the guys that did this and share some of the results. The Astro PH link for the paper is here, and it's also been accepted for publication and monthly notices. So that's a great deal, great news for the authors, and like I said, just a fun result for the GBT, getting to discover a pulsar way down at -45.5 degrees declination. So that was a lot of fun. Other activities coming on, we got August 144 meeting coming up very soon now, September 22nd to 24th. Again, this is all online, and I encourage you, if you're interested in this, to go online, take a look at the schedule, and if you're interested, go ahead and sign up for this meeting. Our observer training workshop in the fall is completely full now, and we've already got overflow on that. The next workshop is scheduled for February 2021. This one's also remote. Information about this can also be found at greenbankobservatory.org. And so if you're interested, or if you have students or colleagues that are interested in getting trained to use the GBT, we strongly encourage you to sign up for our February workshop. And then finally, of course, we will be having the annual single dish school, again with Arecibo, as we did last year. This is tentatively scheduled for May of 2020. And I apologize, I know I said details coming soon 2 weeks ago, but we are working on the details for this and should have those up and running soon. So with that, as always, I'd like to thank you from all the scientific staff at Green Bank Observatory for attending these. And I'm going to stop sharing now and go ahead and hand this over to Brian Mason. I will say that if you have any questions during Brian's talk or any questions about what's going on with the GBT, I encourage you to use either the chat or Q&A function, and we will make sure that the speakers see those questions. So I'm hoping that Brian is grabbing the screen share right now, and there we go. So I'll stop talking and hand it off to Brian Mason. Thank you.
Okay, Faye, thanks. Thanks for that, and thanks for giving me this opportunity. Let me just, okay, that's fine. Can you hear me? Everyone hear me?
Yes.
Okay, great. I'm going to talk today about some work we've done in the past few years with the GBT at 3 millimeters, as well as some other telescopes that I'll talk about towards the end. Just 1 second here. This is work done with a number of collaborators who I've listed down below, and you may also be graced with an appearance from my 2 other second grade collaborators who are here as I'm speaking virtual learning. So I'm going to talk about long wavelength measurements of interstellar dust in Orion. Why do we care about dust at long wavelengths? The main reason is it's commonly used as a mass tracer, other than its sort of intrinsic interest as an important factor in star formation in the interstellar medium. As a mass tracer, 3 millimeters is pretty useful. Sort of long millimeter wavelengths, generally speaking, are pretty useful insofar as the opacity is lower, reducing the optical depth is a systematic that you have to deal with, and producing mass estimates, and instrument sensitivities and fields of view tend to be better. The caveat with using dust as a mass tracer is, of course, in order to derive masses, you need to understand the dust physically, at least to the point of knowing its opacity. So this is just an illustration from Ossenkopf and Henning of how the dust opacity can depend on the grain composition and structure of the function of wavelength. And this red line here shows the commonly employed approximation that at millimeter and submillimeter wavelengths, the dust opacity is a power law. That is, of course, an approximation. And this is just an example. This is an ALMA project targeting dense pre-protostellar cores found in Apex Laboca 870 micron survey. These are ALMA band 3, that is to say 3 millimeter observations. And these are fantastic results, and they also depend on understanding dust emissivity to derive the masses of these cores. And if those were to be wrong, our estimates of the mass and the dynamical stability of these pre-protostellar cores would be impacted. So it's with that in mind that a number of years ago, actually about a decade ago, a colleague named Scott Schnee undertook a survey of the Orion so-called integral-shaped filament, also known as OMC-2-3, at 3 millimeters with the Mustang bolometer camera on the GBT, that is the sort of predecessor to the current Mustang 2 camera on the telescope. The integral-shaped filament is one of the nearest active star-forming filaments that has both low mass and high mass star formation, and it is blessed with an abundance of multi-wavelength data. It's very well studied. There are catalogs of starless cores, protostellar cores, young stars, and just a ton of data to aid in interpretation. So this is the observation we did a number of years ago, shown on the right with the GBT at about 9 arcsecond resolution at 3 millimeters wavelength. And we combined that with Mambo data at 1 millimeter, which yielded these surprising results that the opacity, excuse me, which is typically characterized by this power law beta, was actually significantly flatter than expected. The typically seen opacities for dust in the interstellar medium are in the range of sort of 1.5 to 2 or even steeper. But comparing Mambo and the Mustang 3 millimeter emissivity, so between 1 and 3 millimeters, we saw emissivities closer to 1 and even to as flat as 1/2. So that was quite surprising. We checked a lot of possibilities, sort of systematic errors, miscalibration, spinning dust, and ruled them out as possible causes. One second. And so this was these were results that were reported in Schnee et al. 2014. That work was carried further and put in a broader context by Sarah Sadavoy and collaborators in subsequent years. These are some figures from her paper, her 2016 paper, where she brought Herschel data from 160 to 350 microns to bear, as well as getting new 2 millimeter gizmo observations. And what she found was, in fact, that if you look at the short wavelengths, the dust opacity behaved more or less as expected. So a dust opacity of about 1.7 is seen in the filament and in structures in the filament. But it's mostly between, basically, it's the long wavelength, the 3 millimeter data that seem elevated. So we did some subsequent investigation, looked at archival ALMA data, and we were able to confirm that the fluxes we see are consistent with fluxes seen by ALMA. So this really does seem to be a real effect, but it's just a bit of a mystery as to why it's turning up like that. To further follow that up, in winter of 2016-2017, excuse me, we were commissioning Mustang 2, and we took a quick 1-hour commissioning observation of the source of the integral shaped filament with Mustang 2. That's the bolometer camera currently operating on the telescope, and obtained in that 1-hour exposure the map shown on the left. This data has had its calibration firmly tied to ALMA, and we see again that the results are totally consistent with the previous results. So we subsequently added to that deep 1 centimeter photometry of 24 locations in the filament and structures in the filament with the GBT at 1 centimeter using the calcite continuum backend. And so that's also part of this, the results I'm going to present. And basically, we see the same thing. We see the 3 millimeter emissivity is it's a little bit high, and we see that this enhanced emissivity continues all the way out to 1 centimeter, where we clearly detect these structures as well. And so these are just a variety of SEDs. We call them slices. They're just 4 of the 24 regions we selected for detailed study. And this shows their spectral energy distributions from about 1 centimeter to just upwards of 1 terahertz. So we find these are poorly fit by conventional single power laws, but they're well fit if we allow a second power law breaking at about 2 millimeters, just short of 3 millimeters. And the general trends are about as would be expected based on conventional dust grain models. The beta value decreases towards denser and more evolved structures. The temperatures increase towards denser and more evolved structures. Of course, the beta prime is this long wavelength break, and we don't understand that. But it does appear to get steeper towards less evolved structures. We've looked at a number of interpretations. So first of all, just empirically, the 3 millimeter intensities are not quite a factor of 2 above the standard power law extrapolation. And at 1 centimeter, they're about a little over a factor of 5 above the standard power law extrapolation. It is not within the range of plausible calibration uncertainties, which are about 10%. We verified that with ALMA continuum data. The GBT beam is also quite stable and well characterized, and holographically corrected several times during the night through facilities that exist at GBO online. We looked at spectral line contamination. So one thing to note is that both the Mustang and Mustang 2 results agree, even though they have very different band passes. So we also inspected public ALMA spectroscopic data, and there's no plausible source that could account for this. So just two final, sorry to move this thing around, two possible contributors or explanations are anomalous microwave emission, also known as spinning dust. The problem with anomalous microwave emission is that it typically, peaks at frequencies between 20 and 50 gigahertz. And so by 3 millimeters, it's rolling over. So in short, we don't really see that shape. Although in very dense or strongly irradiated regions, maybe different physics can be at play, sort of TBD. Another interesting possibility is there are sort of specific models of dust grains involving amorphous silicate grains, which predict just such a break in the opacity at long wavelengths. So the opacity sort of stops decreasing as rapidly at long wavelengths. So this shows the emissivity of dust grains as a function of wavelength in one such model. So the relevant temperatures for us are sort of in the 10 to 17 Kelvin range. And they show a break qualitatively like what we see. But if we try and put that on a quantitative scale, the amorphous dust models can't on their own fully account for what we see at both 3 millimeters and 1 centimeter, nor can the AME models. This shows, so just a couple of comments about this. The X's here show the excess, the SED excess above what is expected from a fit to the short wavelength data for the individual 24 regions we looked at. And the boxes and error bars are the average of those. So we tried to fit those with these excesses with amorphous dust and AME models, and neither alone can account for it. It is possible that both of them together could explain it. So I'll just comment briefly here. I don't have a slide for this, but we also, of course, looked at free, and that can't account for it either. Of course, many of the regions we're looking at have no known free sources. They're just general interstellar dust in the filament. So we have a fair number of ongoing efforts following this up. We have several efforts being led by Sarah Sadavoy involving ALMA and the VLA, and as well as NOEMA. And I'm going to talk in the next couple of slides just briefly about work we're doing to bring to bear 1 millimeter to 3 millimeter data from the Atacama Cosmology Telescope, as well as ALMA, the goal of which is to measure the long millimeter wavelength dust SEDs over 3 orders of magnitude in spatial scale. And we have a submitted GBT proposal in support of this project. And just in general, the overall idea of this is to look and see if this anomaly exists in other regions, and if it persists to smaller or larger spatial scales and different density regimes. So this is a map from the Atacama Cosmology Telescope showing the larger scale dust emission around the whole Orion complex. The whole region that I've been talking about so far, the integral shaped filament, is shown in the little box in the left-hand inset. And this is, these figures were prepared by Ian Lowe, who was pushing this work forward, looking at the spectrum of the dust over much wider areas using ACT data. And we also are in the process of bringing to bear ALMA data. This is an example showing in the left, again, the ACT 90 gigahertz map with the inset showing the integral shaped filament. The middle is ALMA data that we have in hand. This is a ALMA 12 meter plus 7 meter mosaic of the integral shaped filament. And you can see there the effect of the missing short spacings. And in the right-hand panel, you can see the map that we get when we when we combine the GVT data with that ALMA data. So our goal is to map the overall emission and measure its properties over the entire region, and also to bring to bear public ALMA data and combine it with the GVT data, as well as data that Alvaro Hikar and our other ALMA collaborators have on this target. So in conclusion, we see significant thermal dust associated emission at 3 millimeters and 1 centimeter that is well above levels expected from extrapolating power law opacities from shorter wavelengths. We see this with multiple instruments, both the GVT and ALMA. It could be due to higher emissivities at long wavelengths, but existing amorphous silicate models don't appear to fully explain the SEDs. Although I would say that a more quantitative and more physical examination of that parameter space is really needed. AME could play a role, but again, the expected SED, the expected AME spectra can't fully explain what we see. And again, better models and more centimeter wave data are needed. And we're interested in seeing whether this is due to some peculiar conditions, sort of particular conditions in OMC23, which is very dense, or if we see it in lower density regions farther from ionizing sources. So I'll stop there and take questions. I think.
Yeah, we have a few questions on there. So again, if you could use the Q&A on this, that would be great. So Brian, I'll go ahead and read out the questions to you, and then you can answer them for those that can't readily see the Q&A. So the first question is, are there regions showing normal steep betas?
That's a good question. I would have to look back at our results in detail. I mean, it's certainly the case that there is some variation in the amplitude of the break and its sort of significance. So there are certainly regions where a break in the beta is not detected at high significance.
Next question says, thanks for showing these very nice results. Please, could you comment on the possible impact of the temperature gradients and the presence of very cold dust on the derivation of beta?
That's a good question. So you're saying if there is very cold, I mean, so the temperatures are fairly cold as it is. If you're suggesting that the sort of a significant fraction of what we see could be due to very cold dust, it would really have to be very cold, right? Sort of below 3 Kelvin. So that's a good question. I think it could be looked into more detail, but it's hard to account for the break that we see with cold dust.
And then the last question I currently see on there, do the dust modelers satisfy the Kramers-Kronig relation?
That's another good question. I'm really not an expert in the dust models, so I would defer to someone who is an expert in the dust models.
Okay. All right, with that, I will also thank Brian very much for this. Thank everybody for coming. Oh, wait, there's another question. I always speak too fast. Next question. Do you plan to compare the dust absorption you see in J, H, and K bands? Compare with dust absorption you see in J, H, and K bands?
We don't have any current plans to look at dust absorption, but it would certainly be interesting to do. In particular, these are very, very dense regions. So the extinction would be really high.
All right, so with that, I really will put it into the questions. Thank Brian very much for the fantastic talk. We really appreciate it, and invite all of you to keep an eye out. We should be having another one of these talks in about 2 weeks. They've been great for me to hear about all the great science that's going on in the GBT, and I hope all of you enjoy them too. Thank you very much. Bye-bye.